my name is Ogo, and my research is focused on the properties and impact of atmospheric aerosols such as soot on our climate. So aerosols are tiny particles suspended in air that contribute or play an important role on the Earth's atmospheric system. And soot is a type of aerosol that's released from the incomplete combustion of fossil fuels and biomass burning. Unlike most aerosols which scatter light and cool the temperature of the Earth, soot strongly absorbs light and contributes to global warming. When soot particles are released into the atmosphere, they interact with other aerosols, and these gases can condense on the surface of the aggregates and cause structural changes. Changes in structure affect the ability of soot particles to scatter and absorb light. And when this happens, it makes it harder to quantify. When optical models try to quantify contributions of soot particles on our climate, they usually simplify them as spheres. And as you can see from these images, soot particles are not spherical. So this simplification introduces significant errors in estimates of global warming by soot particles. Additionally, the mechanisms behind this structural evolution are not well understood. So the central focus of my research is to try and improve the representation of soot particles in climate models. And to do this, I need to understand how the structure and composition evolve when the particles are released into the atmosphere. And in order to make it feasible for incorporation in climate models, it's better to work with parameters that can describe these changes. And to develop such parameters, I need to identify the factors that control property changes in soot. And so the rest of my presentation is focused on trying to address or to show you my progress in addressing the highlighted objectives on my screen. So here's a picture of my experimental setup, and on the right is a schematic. I generate soot by burning natural gas in a very controlled environment, of course, and you can see the tiny flame here in the picture. So the generated soot particles are dried to remove water vapor and then size selected, after which I expose them to supersaturated vapors of coating materials that are representative of aerosols and gases that are in our atmosphere. I can check the effect of these coatings by taking high resolution images using electron microscopy. I can also conduct online measurements of size using a mobility analyzer, mass using a particle mass analyzer, number concentration with a condensation particle counter, as well as optical properties using either a nephelometer or a spectrometer. And so for my experimental results, I went through a variety of chemicals, and as I said, these materials are representative of aerosols and gases that are currently present in our atmosphere. And as you can see, I chose a wide number of chemicals with functionalities, physical and chemical properties to try and cover a wide range. And so here are my experimental results. My data is expressed in terms of what we call a growth factor by diameter as a function of growth factor by mass. And so GFD simply means the ratio of the coated soot particle to its initial or uncoated state. And here you see that this diameter or this ratio is always less than 1. The reason for that is that the presence of the coating on the surface of the soot aggregate actually causes it to collapse. And so the collapsed diameter is always smaller than the initial starting diameter. And so this is why this ratio is less than 1. And so for all the materials I used, I noticed that I had two very different groups. For one group, you see this gradual change in structure as you increase the mass of the coating. And for the other group, there's this very rapid change. And so for this gradual change, this dependency has been reported in literature and is well known. However, this rapid change for a very small mass of coating was not expected, and it really puzzled us. And my images also confirm these same online results. So we set out to try and figure out why a very small coating mass would cause such a significant structural collapse. And so we started first by examining our experimental results as a function of the properties of the materials we use. And we focused on surface tension, primarily because surface tension has been described as the go-to reason for why soot aggregates collapse. And so when we plotted the results as a function of surface tension, you can see here that materials that have the same surface tension exhibit very different structural collapse. And so surface tension doesn't explain why such a significant restructuring is seen at very small condensate mass. When we plotted our results as a function of vapor pressure of the materials, we see that same split again. And so materials that are very volatile cause significant collapse, and materials that are not very volatile don't cause as much collapse for the same amount of coating mass. And so we can explain this using a simple cartoon, for example. If you zoom into a soot aggregate, you see that it's made up of tiny spheres that are connected together. So if a material is very volatile, it's likely to evaporate off the curved surface. If it manages to condense in the junctions between the tiny spheres, it might get trapped there. On the other hand, materials that are not very volatile, it doesn't really matter where they condense. They will stick wherever you place them. And so what we think is happening is that we have two very different coating distributions. And so for materials that are very volatile, all of the condensation happens exclusively in the junctions between the monomers. And for materials that are not very volatile, the coating is spread uniformly across the entire aggregate. And so if you take that same 10% coating mass and you place it only in the junction, you have this 8 nanometer thick ring, which is enough to basically collapse the aggregate. If you take that same 10% coating mass and you spread it uniformly across the aggregate, you have this tiny 0.3 nanometer shell that's not going to do much. And so if we plot our results, again, in terms of these radii that describe the coating distributions, we see that they eventually converge only when there is material in the junctions. In one case, it happens really fast because it's direct. In the other case, it takes more time because it's spread evenly across. And so we decided to try and describe these experimental results in the form of a model now. And this model basically checks competition between one kind of condensation behavior versus the other. And both models show that both distributions are dependent on a parameter we call chi. And chi is a function of what we call Kelvin length, described here, the radius of the tiny sphere, and the vapor supersaturation of the material. And what we see is that chi is much lower than 1 if the material is not volatile, and it's close to 1 if the material is volatile. And one of the reasons why surface tension was not such a big deal is because its effect is secondary. It's basically buried inside the Kelvin length here. And so when we calculated chi for our various coating materials, we realized that it does a pretty good job at predicting, one, what kind of coating distribution we have and whether the aggregates collapse or not. And so
2 minutes left.
Thank you. My model results are expressed in terms of reduced condensate as a function of reduced time. So if the material is very volatile, chi is close to 1, and you see here that only condensation in the junctions is preferred. If chi is close to 0 for the low volatile material, conversely, most of the condensation is happening only on the surface of the spheres. And so this chi actually does a really great job in telling us, one, what kind of distribution we have, and two, whether the aggregates collapse or not. If we vary the radius of the primary and keep our vapor supersaturation constant, we also get very similar results. Basically, we know what kind of distribution we have, and we know whether the aggregates will collapse or not. So in conclusion, what actually drives or causes the particles to collapse is whether we have material present in the junctions. And this distribution of the coating is controlled by how volatile the material is embedded inside here, which is a function of the vapor supersaturation. Also, the effect of surface tension is not really the go-to parameter. It is actually secondary because it's buried in this LK term here. And finally, this chi parameter does a pretty good job in describing, one, what kind of coating distribution we would have, and whether our aggregate would collapse or stay in its original state. And so it's a very simple model and can be easily incorporated in a larger climate model. And my next step is to see how it affects optical properties. And so at this point, thank you for your time, and I'm happy to take any questions.